Hello, I'm Yoon, and I'll be presenting our work on boosting vision transformers for image retrieval. Vision transformers have achieved remarkable progress in vision tasks such as image classification and detection. However, in instance-level image retrieval, transformers have not yet shown good performance compared to convolutional networks. We show that a hybrid architecture is more effective than plain transformers, by a large margin. We introduce two branches collecting global and local information, from which we form a global image representation. Our contributions. First, we collect global and local features from the classification and patch tokens respectively of multiple layers. Second, we handle dynamic image size at training. It called dynamic position embedding. Third, we enhance locality of interactions in the last layers by means of lightweight, multi-scale convolution. Fourth, we contribute to fair benchmarking by grouping results by training set and training models on all commonly used training sets in the literature. Fifth, we achieve state-of-the-art performance on image retrieval using transformers for the first time. There are two ways to form patch token embeddings. The most common is to decompose the input image into raw, fixed-size, square non-overlapping patches and project them via a learnable linear layer. Our model uses a convolutional network stem to map the raw input image to a width by height by dimension feature tensor, then fold this tensor into a sequence of width by height vector of dimension d. A transformer encoder processes a sequence of token embeddings by allowing pairwise interactions in each layer. Global branch takes as input the multi-layer CLS features and embeds them in n-dimensional space using a fully connected layer. Local branch takes as input the multi-layer patch features, containing rich spatial information. We apply one-by-one convolution to reduce the number of channels effectively. Then, we apply our enhanced locality module. And we fuse with Y, choosing from a number of alternative functions studied in the supplementary. We obtain an n-dimensional embedding from the local branch by global average pooling over the spatial dimensions, followed by FC layer. Finally, we obtain a global n-dimensional image representation by concatenating local and global branch and applying dropout, FC layer, and batch norm. This figure is the proposed enhanced locality module for improving locality. ELM consists of an inverted residual block followed by atraspatial pyramid pooling. IRB is wrapped by two wave block layers, serving as feature-level augmentation. IRB is a lightweight convolutional layer, where convolution is separable over the spatial and channel dimensions. ASPP acquires multi-scale spatial context information. When image size is different in each mini-batch, the input resolution is different. How can embedding change size while being learnable, that is, maintained across mini-batches? We address this inconsistency by actually representing the position embeddings by a learnable matrix. At each mini-batch, the sequence corresponding to the patch tokens is unfolded, then interpolated and resampled. And finally folded back to a new sequence. We call this method dynamic position embedding. This table shows our main experiments. We are the first to organize results by training set and train a model on all commonly used training sets in the literature for fair comparison. Our model against the state-of-the-art by training set. More information and further qualitative results we refer viewers to our full paper. Thank you for your attention.